In this video, I would like to go over coming up with a model, a formula that describes a particular graph or a particular set of data. So the set of data that we have is going to be the data that is graphed here in this particular picture. So I'll make a couple observations about it. And to do so, I'm going to copy this over. Oops. So if we look at this particular graph, you can see a couple of things going on here. One thing is that it's oscillating. So we have this up and down, up and down, up and down behavior. But also the amplitude is growing over time. It's getting taller and taller and taller. So if we observe this, let's check to see if our period is consistent from peak to peak. So if I make a line segment from here to here, that would represent the period, the horizontal time, if you will, of how long it takes for this particular wave to repeat itself. So if we slide that over, then notice that's the same distance from this peak to that peak, this peak to that one, this peak to that one to that one, and so forth. So from one wave to the next, we have a consistent oscillation. Our period is the same throughout. So if we're graphing something that has a constant oscillation, we can graph that as a sine wave or a cosine wave. In this case, it would probably be best to graph it as a cosine wave or model it as a cosine wave because it starts at a peak. So we start at a peak, end at a peak, start at a peak, end at a peak. So remember that generically, a cosine wave is A cosine Bx plus C, and then all of that is plus D. So the one that we have here, it's centered vertically on the x-axis, so it has no vertical translation. So D is 0. We will come back to the amplitude later, so let's not worry about the amplitude. And there's no horizontal displacement because we're starting at a peak. So B has to do with the period. And remember, the relationship is that the period is 2 pi over B, or B is 2 pi over the period. So if you know one, you can get the other one. So if we look at our wave, then we can approximate what our period is. If we come back here, let's notice that this period starts here and ends here. That looks to be roughly 2.5, or if we look from here to here, notice this peak looks like it's right at 5. This one's right at 0. So from 0 to 5, we have 1, 2 oscillations. So yes, it looks like our period is about 2.5 units. So what does B need to be? Then B is 2 pi divided by the period. So in decimal format, what would that be? 2 pi, 2 times pi over 2.5. That's about 2.513. And can't always trust my own typing. So for our cosine wave, if it was just cosine wave, our model would be y equals cosine of 2.513 times x. So that would take care of the oscillation part. But it's not just oscillating, it's also growing. So one question is it growing linearly, or is it growing exponentially? If we were to try to draw a straight line through those peaks, notice those peaks are not in a straight line. Those peaks are actually, over time, that rise is getting steeper and steeper and steeper. So the peaks, we could say they have exponential growth. So it turns out if we could come up with a function for the exponential growth of that in terms of y equals ae to the rt, then we could multiply that times our cosine. This part would take care of the oscillation. This part would take care of the exponential growth. If you think about how's that going to work, every time we go through a complete cycle, cosine oscillates between -1 and +1. At the beginning of a cosine wave, we're at 1, so this part is going to give us the amplitude. That times 1 is itself, so the amplitude is going to be determined that part. This part is just going to strictly determine the oscillation. So how are we going to go about getting that? So to begin, we need to select a few specific points off of our wave. So we're going to look at the peaks of our curve and see if we can kind of come up with a trend or something for them. So let's go into Excel and let's look through our data and see when we have peaks. So the first peak that we come to is where we start. Remember, our wave starts at a peak. So our first peak is here. So I'm going to call these peaks. So our first peak is 5. And then just looking at the picture, we go down, we get to negative y values, and then we go back up to a peak. So if we look through our list of heights, we're at negative heights. Now we go back to positive heights. And before we start going back down in this region, this is the largest y value. So that would be a peak. So I'm just going to do equal that one. So that corresponds to that peak. So then I start going down, I go negative, then I go back positive, and the next peak I come to is here. And then the next peak is here. And then the next peak. We're just going to go through and grab each one of these. And for our oscillation, that's the last peak. Now, this one may or may not be a peak. We don't know for sure. It looks like we would still be going up, so it looks like the next peak would be here. So we're not going to include this one, this value here. So let's graph that alongside this particular data. So let's click on this and let's select some data. So we're going to add our x values. Those are going to be the times that correspond to these peaks. So we have this one, and I'm just going to hold down control. So the next one will be here. Scroll. And here. 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 And here. So those are the times, the x values, and then we just need the corresponding y values. Oops. Clicked off. Did I lose one? Well, let's make this a little easier. Let's cancel that. So if I drag this over, this is going to give me the corresponding, no, it's not. Let's grab the corresponding value there. So this is going to be that value. And we want to grab those two. We can go down to each one of these, paste, and it's going to give us both values, not just one. So come down here. All right, so now in this column, these are our x values. So these are the times at the peaks, and these are the peaks. So now we can come back and insert those. So select the data. We're going to add our x values are going to be these times. And even though there are empty cells in there, that's fine. And then our y values are going to be the ones right beside it. Want to make sure that however far down we went on the left, we go that same distance on the right. So notice there's a dot at each peak roughly. If we wanted to, we could even come in and can hide one of them. So now we're just seeing those peaks. So let's look at something interesting about an exponential. So if we have y equals a e to the rt, one thing that we do from time to time is we take the log of both sides. If we want to solve for something in the exponent, we take the log of the left and we take the log of the right. When we have a product, we can split that into the log of each piece. So log of the first factor plus log of the second factor. We can bring the exponents in front of their logarithms. And I'm going to rearrange this a little bit. So I'm going to put the RT in front of log E and then put log A on the end. And let's see, our variables here are Y and T. So I'm going to rearrange these a little bit. I'm going to put R times log E in the front, and then I'm going to put the time. So notice this somewhat mimics y equals mx plus b. This is a constant. A, that's just the coefficient of the exponential. This is a constant. The rate is constant. Log of E is a constant. T is our variable. And then log of Y, that's a variable. So in the Y direction, we have log of our variable. In the horizontal or in the T direction, we don't have log of that. So one thing that we do sometimes in analysis is do what's referred to as a log-log plot or a semi-log plot. And when you're doing a log-log plot, you're converting your axes from regular values into exponential or logarithmic values. What do I mean by that? If our scale normal values is 1, 2, 3, and this would be 0, and then vertically we have 1, 2, 3. Then if we convert to logarithmic scale, and usually when we do that, that's going to be base 10, then each value on our axes are actually 10 to these powers. So this first value, instead of being at 0, this is going to be 10 to the 0, which is 1. This is going to be 10 to the first, which is 10. Then 10 to the second, which is 100, and then 1,000. And the same thing in the vertical direction. This is 10 to the 0, so 1, 10 to the first, so 10, 100, 1,000. Now, since our data doesn't go to 1,000 in either direction, and this was supposed to be 1,000 here and 1,000 here, I didn't put enough zeros, then we would zoom in on this significantly so that our data fits on there. Well, in our case, we're only exponential or logarithmic in the y direction. We're linear in the x direction, in the horizontal direction, because our variable, we're not taking log of it when all things are said and done. So if we come back to our Excel and we adjust the scale, we're going to leave the x-axis in a regular scale. We're going to click on the y-axis and we're going to adjust the scale of it. I can select these. We're going to adjust to a logarithmic scale. Notice it says base 10. So notice when we do that, these are in a straight line. We can verify that by copying this over. And we can draw a straight line and it goes right through those points. Now, they may be off a little bit because when we looked at our peaks, not every point was exactly on the peak, but it was very, very close. So we can use this information to actually find out something about the values that we need. Cut this stuff back. So what do I mean by that? If we can determine the slope of our semi-log plot, and why semi-log? Because we're only looking at the log in one direction, then that slope corresponds to r times log of e. If we can determine the y-intercept of it, then the y-intercept corresponds to log of a. So if we want to find r, we can divide both sides by log e. So r is the slope divided by log of e. And let's see, this is base 10. So if we want a is 10 to the b power. So we can use that to get our coefficient here and to get r here. Now, you might think, well, isn't there an easier way to get a? And there is an easier way to get a, actually. If we were to go back and look at our graph, and let's see if we can go back a little, then what is one thing we know? We know that when time is 0, this part would be 1. That's going to be at a peak. So A is also corresponding to the initial height. So if we could read off of the graph what our initial height is, then we could get A. Or if we could go to our data, which we can, then our initial peak is at 5. So in our case, without having to do all of this, we can get A. A is going to be 5. So we know that part already. But we are going to need to use this formula in order to get R. So then the question becomes, well, how do we get the slope? Because this is not just a regular graph with a regular coordinate system, it's a semi-log plot. So let's go back to our plot. Here and copy this again. So normally when we get slope, we pick 2 points and we need to get the rise between those 2 points and the run between those 2 points. So I'm going to call this time 2, and I'm going to call this time 1. And even though this y value, if we were to read it off, is the actual y value, since this is on a log plot, then that is somewhat related to log of that time. And I say somewhat, it is directly related to log of that time. When we're on the regular coordinate system, then it's not a straight line. But when we adjust it, straight line. So in order to get the slope, the height is the difference in the y's, so log T2 minus log of T1. And the run is T2 minus T1. Slope is rise over run, so log of T2 minus T1, or you may recall when you subtract logarithms, you divide their inputs over the run, which is T2 minus T1. And I'm sorry here. I said log of T1. It's actually log of the y value here and log of the y value here. For time's sake, I'm not going to go back and redo this or edit this video. But this is log of the corresponding y value. So for this point, if we just call for random this time 1 in the x direction, then the y value there is y1. Since we're on logarithmic scale, we could think of that as being log of y1. And same thing here, log of y2. So if we came over to Excel, if we wanted to calculate the slope, then we could do the calculation where we take log base 10 of, and let's just pick 2 points. I'm going to pick the second point and the fourth point. So what are we taking log of? We're taking log of the y values. So the log of the y value here over the y value here. So that's what we're taking log of. And then we're dividing that by the difference of the times. So make sure I've got all my parentheses. So we're taking log of that quotient divided by the difference in the times. So the later time minus the earlier time. So that's the run. And when we calculate that slope, we get 0.077326. Now, if we look back, how do we get from there to R? So R is that slope divided by log of E. So we could do that in a calculator, or if we're doing it in Excel, the way we do that is we do equals, we click that value, and to take log of E, we do log base 10 of, to get E, E is exponential, and E to what power? E to the first power. So that's this value divided by log of E to the first. So it looks like this is going to be our R. Now, in a perfect world, then that would be the exact value that we need for R. But remember what we did is we randomly selected 2 points on our graph, and we calculated the slope between those 2 points, but it might not be perfectly in a straight line. In fact, when we drew a line through it earlier, some of the points were a little bit above the line, some of the points were a little bit below the line. So there's a technique called the least squares approximation, statistical analysis, where we can find the equation of a line that best fits that. So there are different ways to do it, but what we can do in Excel, since our y values are in a logarithmic scale, we can take log of each of our y values. So I'm going to come in here and say, I want the log of the peaks. So in these values, I'm going to take equals, I'm going to do log 10 of my y value, my peak, and that's going to calculate the logarithm of 5. I want to do that same calculation for each of my peaks. So I'm just going to copy that, and I'm going to come down here, I'm going to paste that, and I'm going to do that for each peak. We could just drag that formula down, but there are going to be a lot of gaps in between there because there are a lot of spaces between each peak. So I'm just going to individually go and on each peak, I'm going to paste it in. So this column is just the log of each peak. So Excel will calculate the slope for the using the least squares approximation. Least squares. And the way we do that is we type equals slope, and then we highlight the y values. So in the y direction, those are actually log of the y values, comma, and select the x values. The x values are just the times, not the log of the times, but just the times. Because remember, this is a semi-log situation where we're taking the log in the y direction, but not log in the x direction. So when we do that, we get this slope. So notice there is a little bit of difference between those two. This was using 2 points. This actually takes into consideration all of the points. So then recall that to get R from that, R is the slope divided by log base 10 of E to the first. So we calculate that, we get 0.125075, or we can call that 0.125 as our R. So we determined earlier that A is 5, R here is 0.125. So the exponential part of our model is 5e to the 0.125 times t. We can take that and multiply it times the oscillating part, which comes from the cosine, and we took cosine of what? Cosine of 2.513. Cosine 2.513 t. So let's check to see if this formula, if that model actually does what we think it does, if that actually approximates our data. So how are we going to do that? Well, let's use Excel. So I'm going to come in and I'm going to put in the A. Let me see, I want to add a row in here. So I'm going to right click here and insert a row. So my A value, my amplitude is 5. My rate, or our rate, we got is 0.125. And our B, which is the coefficient of t that we're taking cosine of, 2.513. So we can get our model. We can use these same times over here, or we could make another list of times. If we want more points, we could add times. And if you don't know how to make a list of values in Excel, there are several different ways. One, we can set up a pattern. We can start at 0 and say, let the next value be 0.1. If I highlight those and then I come down to the bottom right corner and I drag, then that's going to use that pattern and it's going to copy those cells. So let's go through about 24. Notice it's telling me values. So let's go through times of 24. and we want to calculate our function for each of those times. So our function is our A value, and when we go from the first time to the next time, we don't want that value to change. So the way we do that in Excel is we mash F4. So that when it puts those dollar signs around the K and the 2, then it's going to use that A every time. We want to multiply that times E, so exponential, and E of what? Our rate. We want to use that same rate every time, so F4 times time. Now we're going to use a different time each time, so we don't put F4 there. And then times cosine of our B, using the same B each time, times time, using a different time, so we don't F4 there. So I hit enter, notice I get 5 for that, which that corresponds to our time and height for our actual data. So if we click on this and drag down, then it's going to calculate our function value for each of these times. It's going to leave A, R, and B the same. It's just going to put different time values in. So let's copy this through our last time. And then let's add this to our chart. So we can come to our chart. Let's turn off the logarithmic scale. Let's turn back on our other data. And then, so let's not draw lines through it because our actual data points that were collected are just the dots. So we should be able to format that. We can change the chart type, and instead of having it a scatter plot that has lines through it, we can do it as just a regular scatter plot so that it just has the dots and not the lines through there. So we can add some data. So our new data, the X values are going to be the times that we brought down over here. So from 0 to 24 seconds. And then our Y values will be the corresponding answers to our function. For that one, let's adjust what type of plot that is. For that one, let's put lines on it. So it's a little bit hard to tell, but the blue dots, those are our actual data points. I'm going to zoom in a little bit. And then our gray curve, notice it goes through those points. So it looks like that our model seems to have the right period. It's oscillating with our data points. And it seems to have the correct exponential growth because our peaks and our troughs are hitting at the same place. So this is just a technique that we can use if we have data that has an oscillation in it and has an exponential growth or exponential decay to come up with the equation that actually goes through those data points.